Let's talk about how we do threading in Simics and then how we apply this to SystemC in a bit of a backhanded way, I would say. No, wasn't the right. Let's see. Yay! And let's test laser pointer. You can see it, right? Yeah, okay, let's move on. Yeah, and the interlegal notice. Threading in the Simics simulator. So what we've done in Simics has been, we have been working on threading out our virtual platform framework since, I would say, late 90s were the first attempts. The first successful attempts happened in about 2005 when we threaded out across separate target machines. And in recent years, we've been adding up more and more threading in Simics because we need it for performance. Our take on this is a bit different. I mean, we want threading to be handled by the Simics framework. We define our own host-independent threading semantics. We define our own thread execution modes. The user is always in control. They can control the number of threads. They can enable and disable parallel execution because, I mean, you want to be able to tune these things depending on where you're running. Fundamentally, threading should affect as little code as possible because we are talking about, I mean, with Simics, right now, I would say we have roughly 100 different instruction set simulator models, probably between 10,000 and 20,000 different device models, and on the order of 100 different virtual platforms in progress right now, maintained by a team of count internal and external users, maybe talk about 300 modelers, something like that. So it's a pretty big business. And fundamentally, we don't want these people to have to understand parallelism because parallelism is painful. I mean, parallelism is hard, annoying, and kind of the, in a way, it's the last resort. If you can't make it run serially fast enough, you have to go parallel. Sorry. So fundamentally, a device model, which is the vast volume of models, should not need to change even if we turn on threading or turn off threading. I mean, we want to provide a virtual nice mode for all the device models, which means that in practice, we have tried to lock in all the parallelism into the instruction set simulators because they take like all the time in the simulation anyway, and a few features that actually need to understand threading, like networking, for example. It's possible to revert a sequential execution on demand because we want to be able to have deterministic execution for software debug, for example. And it really helps to debug models if you turn off threading because then you don't need to worry about concurrency in addition to whatever bugs you have in your model. It's also absolutely clear that determinism is not possible to have if you want maximum performance. I mean, we tried it a number of times and the cost is simply too high. And determinism, strictly speaking, it's not all that valuable anyway, if it means you can't run the real workloads. So it's more important to be fast than to be deterministic. Took me a while. I was very much opposed to this for a decade or more, but I kind of learned to live with it nowadays. And finally, I mean, if you want to go fancy, we do have the APIs available to actually do, full thread programming if you want to. But essentially, threading should be easy, automatic, and invisible to most modeling teams. Some use cases or applications in Simics. I mean, the easy case is this classic multi-machine accelerator. Been doing this for more than 15 years. Where you have multiple separate complete target machines. I mean, this could be like an, Ericsson board in a telecom switch. It could be a one PC in a network. It could be an IoT node. I mean, something like this. We've been doing this with up to 1,000 nodes in our network, for a long time. This is super easy because you have a long latency network and each target machine is essentially isolated because it doesn't share memory, doesn't share devices with the others. So this is, well, not trivial, but this is pretty easy to implement and it scales pretty well as long as you have, like, if you can give the network latency a millisecond or something, you can even do this deterministically. And then we have the hard case, which is when I have multiple processor cores sharing memory working on the same software. And this is the case where all the complicated stuff comes in and it's still pretty straightforward, right? It's a bit like what we saw when we had this, basically matrix multiplication benchmarks on a bunch of worker cores. I mean, it's this case. But then we have what I would call maybe the more important cases, right? If you take a target system, you have a few processor cores, like an Alder Lake or a Xeon, where you have between 2 and 50, 60 main Intel cores, right? They're all accessing memory, work on their devices. And then we also, which we do today, we add in a dozen or so firmware systems using, ARM, ARC, all kinds of architectures are in there. And these guys, we want to kind of parallelize out all the execution in these embedded firmwares because they can take as much time as the big IA cores to run because they are active all the time. So one very important use case is really to kind of kick off these subsystems on their own threads, and maybe it's okay to have round robin between the big IA cores because they're not actually doing all that much anyway. I mean, most of the time, most software nodes do nothing. You have to work hard to get more than a few threads running. I mean, typically you need to be actually running a threaded workload. And finally, multi-threading is a generally useful coding pattern, right? If you have the simulator talking to the outside world, I mean, if you got some emulator, FPGA prototype, physics simulator, other simulator, that thing is not going to care about your nice synchronous execution inside your system. So you need a thread to take care of this. So essentially we have a thread as a way to interface between these different non-synchronized domains. So threading is a general purpose mechanism. And we handle all of these using essentially the same mechanisms in Simics. And of course, we can combine these different use cases. It's perfectly possible to have like multiple subsystems threaded out inside a target system, inside a network, etc. Right? So it's very easy to come up with a lot of parallel work in this way when you have hundreds of CPUs inside your target system. So how do we use threads in Simics? And this is still at a high level, just to explain the concept. So here's your typical target system. You've got a couple of machines in a network. You've got a few processor cores, a few subsystems. And in this case, this is all simulated system. So we carve this up, put in kind of potential threads in here, and then we run this on our own scheduler and kind of, essentially this is a work queue model where the simulator says like, yeah, these things could run in parallel. So I'm kind of, add myself to the queue. And then the scheduler takes care of farming this out to a existing set of OS worker threads. And the number of, threads in the simulation can be much higher than the number of available OS threads, which in turn can be much smaller than the number of available cores, because if you have multiple simulators sharing the same big server, for example, you might say that every Simics only gets 2, 4, 8, whatever threads. So we have to be able to control that in order to efficiently utilize a data center of a simulation. And then, of course, we have some other things, right? The just-in-time compiler in Simics actually has its own little thread pool. And that is actually separate because we kind of trust the JIT to deal with its own threading. And this one can be pretty big in many cases. If you're running mostly serial, most of the parallelism might come from the JIT offload. And as a user, you're also allowed to spin off your own threads. And in this case, typically Simics will allocate a new host thread for you. So there is kind of a pool, worker pool management behind the scenes, but you kind of get your own thread. And if you want to, you can sit in that thread essentially, for an arbitrary amount of time, or you just use it for a short time and kind of hand it back over to the main Simics thread pool. So threading concepts, and this is really the core of Simics threading semantics. So here is a bunch of processors, the one's called proc, we have a bunch of devices, we have memory, and let's superimpose some parallelism here. The first thing we have in Simics is the cell. A cell is the smallest loosely coupled unit in the simulator. Typically, this would be a single target machine, like a single PC, a single server, a single IoT node. Well, something you would physically consider this is a separate machine. Between cells, you have to use what's known as a link to communicate. You cannot just call between these guys. You have to pass through a link, and that link is usually something like an Ethernet network, maybe I2C, maybe serial, but in 99% of the cases, it's Ethernet in practice. And cells are easy to run in parallel because all devices only have local state. That is the Simics rule. You only work in your own dynamically allocated device structure. You have no threads, no stack, no static variables, no silly stuff in the code. I mean, you're supposed to just put all your state into a dynamically allocated structure on the heap. Next, if we want to add a bit more parallelism, we add what we call thread domains. And that is used to indicate, it doesn't mean we have a thread, it means this stuff could potentially be run in parallel in case we have work in multiple of them, and in case we have available worker threads, because you can still tell Simics run this whole thing with only one thread, in which case we serialize everything. Or you can tell Simics to try to grab as many cores as it possibly could. Typically, if things kind of go into a thread domain, they have to be explicitly thread aware. They kind of know that they're going to be out there, kind of flying around outside the safe space, because the safe space is what we call the cell thread domain. And this is some might call it a semantic hack. I mean, essentially what we say is that if you have a non-thread aware model, which could be a device, could be a processor, that thing runs in a special thread domain known as a self thread domain, and only one thread can ever run at any one point in time inside the self thread domain. So there you have virtual serial semantics, right? This one, the self thread domain can run in parallel to other thread domains, but if one of these do an access into the thread domain, it grabs the cell lock, and it will wait if somebody else is active in there. It will wait for that one to finish before it gets in. But if this one is accessing the cell and these ones are just talking to themselves and to memory, which is a super special case, they can still run in parallel. It's also possible sometimes to put some devices out in a thread domain together with the processor. I mean, if this is something like a PIC, it could be one of the very closely coupled controller devices you have along certain processor cores. Sometimes they migrate out into the thread domain, so this thing then becomes kind of thread-aware code. So this one is complicated, but everything in here can be kept very simple, because all they see is a virtual serial semantics, which is exactly the same as when you run Simics in serial mode. No change to the code, no change to the semantics, mostly. So how does this mesh with SystemC? I mean, in Simics, we have the ability to run SystemC models as essentially subsystems. I mean, our idea is that we bring in typically this is used to bring in code from external vendors who provide us with ready-to-use, subsystem models for some reason. And the goal here is that we have to be able to use Accellera compliant SystemC models as is, which typically means some other company compiled the model into a binary with a certain version of GCC and all that other fun. So we have to be absolutely ABI compatible with the standard SystemC kernel, because otherwise things will not end well. So what we do here is that in Simics, every SystemC model, which is now a subsystem, typically this is an instruction set simulator plus a few hundred devices, something like that, right? A subsystem, firmware engine, for example, some kind of accelerator, maybe a network card, maybe a USB device, something along those lines. And we compile them into what we call an adapter. So what we have is a single Simics module, which is a Simics binary distribution format, where we have a SystemC kernel, your own copy. We have a bunch of SystemC models, and then we put them inside what's known as an adapter. And inside the adapter, we have the special co-execute object that kind of ties this SystemC subsystem to the Simics scheduler. And that thing is actually thread aware. So what happens is that we do something like this. You load, in this case, we load module N, and we create a number of instances of class N inside of Simics. And then the question is, so how can these run in terms of threads? And the answer is not as well as you might hope. Because this happens, this is what it looks like, right? Here is one thread domain. I have multiple instances of the same model here. So this is model M in this case. The problem is, due to the way SystemC works, all these models share the same SystemC kernel instance, which means they share state, which means they can't run in parallel, as the previous presenters have already kind of addressed the fact they can't really do this in the plain SystemC kernel. So in this case, we just take the SystemC kernel, just kind of admit that all these models that happen to be the same exact subsystem, well, they just have to run in the same thread domain, which means they will execute, these two co-execute things will execute round robin inside this thread domain. And I can't take that specific SystemC model and put it in another cell, because I am not allowed to share any state between models that run in different cells. So this is a bit of a bummer, but this is due to the fact that we have to be able to run unmodified, binary supplied standard SystemC models from external vendors. We have zero control over the source code. I.e., I mean, that's a standard case, right? I mean, that's how things pretty much always work in industry. But it's still perfectly possible to have other models in Simics run in parallel to SystemC. So this is a good model for parallelizing out. If you have some SystemC language subsystem, once again, you can actually run that in parallel to the main processors in the system and still gain the benefits of parallelization. It's also perfectly possible to have other SystemC models, right? If I have model N or model O, which are separate, that means they're separate Simics modules, which means they have their own SystemC kernel, which means they can run in parallel because there's no shared state anymore between them, right? So this is basically what Ola talked about at the beginning. We have multiple separate SystemC kernels. We just run them inside a single host process, but the semantics are basically the same as if you put these in different host processes. But you can actually, or we have done it to actually instantiate a number of copies of the SystemC kernel inside the same process. So in summary, Simics can run SystemC models in parallel to each other and in parallel to other Simics models. When we access shared state, i.e., if your SystemC subsystem calls out and reads simulated memory, or if it tries to send off an interrupt signal to something, if it receives an interrupt from somewhere else, if it gets a reset signal in, if we pass out some Ethernet packet, all that communication with the rest of the simulated system in Simics requires locking according to Simics threading rules. But this is all handled by the adapter and is actually invisible to the SystemC model that we wrap inside the Simics adapter. Parallelism, as I said, is enabled using multiple separate kernels. And really, this is because we have to be able to use absolutely bog standard Accellera with ABI compatibility. If we allowed ourselves to say, like, let's fiddle a little bit with the kernel, just take out some of the static variables, we could make this more parallel, but that would break the importation of binary models, unfortunately. And once again, inside each subsystem, we have completely standard SystemC serial semantics. And parallelism here really comes from the fact that we would expect to have many different models running at the same time as part of a simulated system. It doesn't work as well if you just kind of creating n copies of something. Of course, you can cheat and you can combine the same model into multiple separate Simics modules. But you can do that, right? It's not the most elegant solution, but it can be done. It has been done. And if you want to learn more and try this, well, the easiest thing is to actually download the Simics simulator. It's open, it's public, it's free. You get a complete Simics-based product, including the SystemC library. We have a simple model in there. And we also have some, thermal and power and performance models as well in this thing. But if you go to this address, you can download this and basically look at the way Simics does threads on its own. I have an example I wrote in there known as Workshop 2, which is doing what I would say is extremely similar to Matthew Moy's way of parallelism, but using the Simics API. Very much the same idea. I mean, basically, in a way, everything Matthew said is very similar to what we do in Simics, except the Simics solution is a bit more rounded because this has been, this is a decade in commercial use. So we have added quite a few features to make this actually work in, real systems with very large simulated systems used for, very aggressive pre-silicon enablement of very complicated hardware. So that's it from my side. I don't know how we are for time. I believe I was fairly short here.
Thanks a lot, Jakob.